Hey everybody, there's one more example of a way to use the addition and subtraction formulas for sine and cosine that I wanted to show you. This is interesting in its own right, and it will show up in a couple places later on in this quarter too. So here's our example. So we have this function f of x is the square root of 3 times cosine x plus sine of x. And what I want to start out by doing is just looking at the graph of this function. So let's pull up GeoGebra and we'll type in f of x is the square root of 3 times cosine x plus sine x. And if you look at this graph, it looks like a shifted cosine graph or shifted sine graph, depending on your point of view. So it's looking like if you just add a cosine and a sine, even with coefficients in front, you actually just get a shifted cosine graph or a shifted sine graph. So let's see if we can figure out why that happens. So I've quite helpfully put the addition formula for sine here. And if you look at the addition formula for sine, it looks like there are some pieces of it showing up here. So right here, this square root of 3, it looks like that's playing the role of sine alpha, maybe? And then cosine of x, I guess that would be playing the role of cosine beta. It's just beta is equal to x, I guess. And then, let's see, in the second part, sine of x, I guess that's playing the role of sine of beta. And then, well, there's not really anything in here to play the role of cosine of alpha, but, you know, there's always a times 1, isn't there? So that 1 maybe is playing the role of cosine of alpha. So this seems like a decent idea to get us started, except there is no angle alpha whose sine is the square root of 3, because square root of 3 is just too big. And, you know, so we don't actually have a good way of choosing alpha right here. So what we should do is maybe figure out what should we divide the square root of 3 by so that this square root of 3 becomes the sine of an angle and 1 becomes the cosine of the angle. You might think, well, if we have a 1 over here for cosine of alpha, maybe we should just choose alpha to be 0, because cosine of 0 is 1. But if alpha is 0, sine of 0 is not the square root of 3. So what we're really looking for is we want to pick an angle alpha so that sine of alpha is the square root of 3 over something. We don't know what to put down here yet, but let's call it c. And so that cosine of alpha is 1 over that same thing. Right? Well, we sort of know a little bit about sine alpha and cosine alpha. These two equations are enough to let us actually sketch our right triangle picture. And let's put alpha down in this corner. It looks like for both of these, c is playing the role of the hypotenuse. And in this first equation, the sine equation, square root of 3 is playing the role of the opposite side. And in our second equation with cosine, 1 is playing the role of the adjacent side. And this right triangle tells us what c has to be. C squared is 1 squared plus the square root of 3 squared. So that's all 4. And so c must be 2. So the thing that we want sitting below this square root of 3 and below this 1 is 2. But how do we make it happen? How do we make the 2 appear there? Well, let's see. So f of x is right? We want to have square root of 3 over 2 times cosine of x plus 1 over 2 times sine of x. Well, you can't just divide everything by 2, right? That would change what the function is. But, you know, you can divide everything by 2 if you also multiply everything by 2. So this, essentially what we've done is we've factored out a 2, and that leaves behind a 1/2. Okay? All right, so we have 2 times. Well, now we've cooked things up so that this square root of 3 over 2 is exactly the sine of alpha. So we can put sine alpha right here times cosine x plus, and this 1/2 right here is cosine of alpha. So this is cosine of alpha times sine of x. Okay, I've made a bit of a mess here. Okay, and according to the addition formula for sine, everything in the brackets here, that's the right-hand side of the addition formula for sine. So we can replace it with the left-hand side of the addition formula for sine, sine of alpha plus x. But to really know what this function is, we should figure out what alpha is. So remember, we had a right triangle where the right-hand side was square root of 3, the bottom side was 1, and the hypotenuse was, now we know it's 2. And right, alpha is this angle in the lower left. And so that meant that sine of alpha is root 3 over 2. Can you think of an angle whose sine is root 3 over 2? Yeah, it's going to be pi over 3. We should check, though, that this gives us the correct value for cosine as well. Remember, we used both sine and cosine to come up with this triangle. So let's check that our cosine value is right. So cosine of pi over 3, is it actually a half? Which the triangle says it should be a half. Is it actually? Yes, cosine of pi over 3 is 1/2. So now we know that alpha is actually pi over 3. So our original function is 2 times sine pi over 3 plus x. So the addition formula for sine showed us that our original function, which remember was a sum of a sine and a cosine, actually is just a shifted sine function. Let's graph this just to make sure that it looks right. So let's graph 2 times sine of pi over 3 plus x. And the blue graph is right on top of the green graph. So if I hide the blue one or show the blue one, it's the same graph either way. And that's just demonstrating graphically that we didn't make any algebra mistakes. So this trick of using the addition formula for sine to combine a sum of two sines and cosines into a single one, but that's shifted, this turns out to be a pretty important trick because there are lots of situations, there are situations where it's better to work with a shifted sine curve, and situations where it's better to shift it with a sum of unshifted sines and cosines. And we'll see that later this quarter. Let me know if you have any questions.